Hello everyone, welcome back to our YouTube channel. In this video, we are going to see about the MOSFET and its operation. First, we'll start with the introduction. The field effect transistor is a transistor that uses the electric field to control the shape and hence the electrical conductivity of the channel of any one type of charge carrier in its semiconductor material. FETs are also known as the unipolar transistors as they will be involving only a single type of charge carrier in the operations. The basic principle of FETs was first patented in 1925 and later on in 1959 at Bell Labs it was invented, that is MOSFET was first invented. That's metal oxide semiconductor field effect transistor, also known as MOSFETs, as the offset to the patented FET design. The MOSFETs or the MOS devices offer very unique properties which has led to the revolution in the semiconductor industry. Metal oxide semiconductor field effect transistors. They are the most commonly used FET. It has three terminals: source, drain and the gate. It is also called as a voltage control switch because the voltage applied to the gate terminal determines the current flow between the source and drain terminals of the MOSFETs, and it is also called as the insulated gate field effect transistors, IGFET. And classifications based on the charge carriers, there are two types, n channel and the p channel, and based on operation there are two types, that is enhancement type and depletion type of MOSFETs. About the structure of MOSFET, fabricated on the p-type silicon substrate, they are also known as the bulk or the body of the device. You can see the substrate is p-type and the device consists of two heavily doped n region for forming the n source and the drain terminal of the MOS, and a heavily doped piece of polysilicon is used operating as a gate, and a thin layer of silicon dioxide insulating the gate from the substrate, hence it is called insulated gate field effect transistor. And this device is said to have symmetry, that is symmetric with respect to source and drain. The dimension of the gate along the source drain path is called length L as it is denoted in the figure, and the perpendicular to the length is the width, that is W. What happens during fabrication is the source and drain regions said to have side diffuse, causing the total distance, that is L, between source and drain to be less than L. That is, the effective channel length will be given as L effective is equal to L drawn minus 2LD. LD is the distance how much it is diffused on each side. There are two sides, therefore 2LD, where EF is the effective length, L drawn is the total length, that is remaining length subtracting 2LD, and LD is called as the diffused length, and the oxide thickness, that is gate oxide thickness, is denoted by TOX. The L effective is as marked in the structure, and also you can check on L drawn and LD. With N type of source and drain and a P type substrate, the transistor operates with electrons, and therefore it is called as the N type MOS, that is NMOS device, and the channel between the N plus drain and source region consists of electron and is formed if only the gate voltage is positive. Changing the doping polarities of the substrate and the source drain, that is now source and drain are P plus and areas and the substrate is N substrate, it will be the PMOS device. The channel consists of holes and is formed only if the gate voltage is negative in this case. So you can see the structure of the NMOS and PMOS respectively and the symbol for the same. ID is the current flowing and the direction is marked as shown. And here are the various representation, I mean the MOSFET symbols, how you can represent NMOS and PMOS in different way. You should be representing the arrow, that is the direction of the current, whether it's PMOS or NMOS, or you can represent it as a the bubbled one for gate terminal bubbled for PMOS and non-bubbled for NMOS. Now let us see the operation of MOSFET. Consider the MOSFET circuit where the source and drain terminal are grounded and the gate voltage is applied. It is varied. As VG, that is the gate voltage, increases from 0, the positive charges on the gate repels the hole in the substrate, thereby creates a depletion region. The positive charge on the gate is mirrored by the negative charge in the substrate as shown here, but there is no channel of mobile charge created and hence there won't be any current flow. Hence there will be the MOSFET will be said to be off during this state, that is when source and drain are grounded and the gate voltage is varied. As the gate voltage VG increases, so does the width of the depletion region also increases, and the potential at the silicon oxide interface, that is if VG becomes sufficiently positive, the free electrons are attracted towards the oxide silicon interface, forming a conductive channel, and the MOSFET will be on at this time. The gate potential at which the channel begins to appear is known as the threshold voltage, that is represented as VTH. If VG, that is the gate voltage, increases further value, the charge in the depletion region remains relatively constant, and while channel charge density increases, providing the greater current from source to drain terminal. And the gate terminal remains insulated from the other terminals due to the oxide, and hence the name insulated gate field effect transistor. Thank you for watching. For more such videos, do subscribe to our channel with electronics tutorials.